Hello everyone, I'm excited to present our work, SumDiff, Generative Modeling of Video Summarization with Diffusion, which has been accepted as a highlight paper at ICCV 2025. This is joint work with my co-first author, Jae-hoon, along with Sumin, Jinhwan, Byung-hak, and our corresponding author, Junseok. Let me start by introducing the video summarization task. The goal is to select a subset of frames that represent the core contents of a video. Given visual information, we predict importance scores between 0 and 1 for each frame to estimate how important each frame is. These importance scores are provided from each dataset with human labels. Now here's the key challenge that motivated our work. There is an inherent subjectivity in video summarization. Different people have different valid opinions about which parts of a video are more interesting. Looking at this soccer match example, one person might focus on the celebration scenes, another on the actual gameplay, and a third person might prefer different moments entirely. All of these are valid summaries, but they're quite different from each other. So, how have previous methods handled this? Unfortunately, they haven't handled it well. Previous approaches take importance scores averaged over all annotators as their target label. As you can see here, they collapse all these diverse valid summaries into a single average score. This destroys the diversity of valid summaries and fails to model the inherent subjectivity properly. This brings us to our key insight. Instead of predicting a single average score, we should learn the distribution of good summaries. We leverage diffusion models to generate multiple importance scores, focusing on the intrinsic subjectivity of video summarization. Just like how diffusion models can generate diverse images of dogs from noise, conditioned on the input video, SumDiff generates diverse importance scores from random noise. This way, we can capture the full distribution of valid summaries. Let me now walk you through how we apply diffusion models to video summarization. Here's our overall model architecture. The process has three main stages: encoding, denoising, and summary generation. Let me explain each component in detail. First, in the encoding process, we extract features from each video frames using a pre-trained image encoder that contextualize them through a self-attention layer. This gives us rich video representations conditioned on the full temporal context. Now let's dive into the denoising process, which is the core of our diffusion model. First, we face a fundamental challenge. Importance scores are bounded between 0 and 1, which prevents us from directly adding Gaussian noise. Since Gaussian noise is unbounded, adding it could push scores outside the valid range. Our solution is to denoise it in logispace. We transform the ground truth scores from 0-1 space to unbounded logispace. In this logispace, we can freely add Gaussian noise to get UT, then learn to denoise it. Next comes quantization, which serves two critical purposes. First, it solves a dimension mismatch problem for cross-attention. We need embeddings that can interact with our video features through dot products. We achieve this by quantizing the noisy scores into discrete bins, then assigning a learnable embedding to each bin. Second, quantization groups similar noisy scores into unified embeddings via the learned codebook. This helps the model learn more stable and discriminative representations rather than treating every slightly different noisy score separately. We cluster them into meaningful groups. Finally, we transform the predicted logis score back to 0-1 space using sigmoid and train the model with a standard L2 loss between predicted and ground truth scores. During inference, we generate importance scores from pure random noise using the DDIM reverse process. Starting from Gaussian noise, we iteratively denoise to produce clean logit importance scores. At the final step, the logit importance score is converted back to importance score applying the sigmoid function. Finally, to convert the continuous importance scores into a binary summary, we use kernel temporal segmentation to partition the video into clips, then solve a knapsack optimization problem. This selects clips that maximize total importance while respecting the target summary length constraint. Just like packing a backpack with the most valuable items within a weight limit. Let's look at our results. We evaluated on 3 datasets, Mr. Heisem, which contains over 30,000 videos from YouTube, and the traditional TVSum and SumMe dataset with manual annotators. On the left, you can see results on SumMe and TVSum. SumDiff achieves the best performance across all metrics. Kendall's-Tau and Spearman-Rho are outperforming all baselines. On the right are results from Mr. Heisem, where we also see consistent improvements. Now here's an important insight about evaluation. Remember that we generate importance scores, which then go through knapsack optimization to produce the final summary. This two-step process creates a critical evaluation challenge. Traditional ranking metrics like Kendall's-Tau and Spearman-Rho only measures how well we rank frames. They don't tell us whether our scores will produce good summaries after knapsack optimization. Meanwhile, F1 score relies too heavily on the KTS segmentation step and fails to show reliable differences between methods. What we really need are metrics that evaluate score quality in the knapsack output space. That is, how reliable are our scores for generating correct summaries? We propose these novel metrics. Confidence of importance score quantifies the risk that our scores will lead to incorrect summary selections through knapsack. Weighted inclusion ratio measures what percentage of scores fall into safe bounds where knapsack decisions are stable. As shown in the table, SumDiff achieves the best CIS and highest WIR shown in the table. The qualitative results really showcase our method's strength. Looking at this example of an obese dog video, you can see two different annotators created quite different summaries, shown by the black and red boxes at the bottom. SumDiff generates multiple diverse summaries that capture this variety, while other methods produce only a single summary that might not align well with all annotators. To visualize entirely, we project all summaries onto principal component space. The colored dots show human annotations while black dots show our predictions. Look at video 22 as an example. The human annotations from 3 different distinct clusters representing 3 different valid ways to summarize this video. Baseline methods produce only a single summary that cannot account for this diversity. In contrast, SumDiff generates predictions that spread across the distribution, closely matching where the human annotators are clustered. This demonstrates our method's ability to capture the full range of valid summaries. This heat map shows another view. For each video annotator pair, we measure how many of our generated summaries achieve high agreement with tau greater than 0.25. SumDiff covers a much larger area of the heat map compared to other methods, indicating we successfully generate summaries that match various annotator preferences across many videos. One important question is computational efficiency. Even with just a single diffusion step, SumDiff achieves a strong performance of 0.717 tau and 0.234 rho, already outperforming baselines. With 10 steps, we reach our reported performance. The training curve on the right shows SumDiff reaches strong validation performance faster than baselines, demonstrating both efficiency and effectiveness. Finally, regarding our quantization strategy, choosing the right number of bins, k, is crucial. With too few bins, like k equals 5, we get overly coarse quantization that collapses diverse scores. With too many bins, like k equals 800, we don't have enough samples per bin for a reliable embedding estimation. To conclude, let me summarize our key contributions. For a generative viewpoint, for the first time in video summarization, we leverage we leverage diffusion models to learn and generate the distribution of good summaries rather than predicting a single average score. Second, generating individual annotations. Due to the generative nature of our approach, SumDiff can generate accurate summaries that correspond to each individual annotation's preference, properly capturing the subjective nature of this task. Third, new metrics for video summarization. We propose novel evaluation metrics that propose the quality of video predicted importance scores through insights from knapsack optimization theory, addressing a gap that traditional ranking metrics cannot fill. Thank you for your attention.